Okay, so let me recall what it is we have seen before, and then we'll continue to plug along. So the wave equation was derived completely mathematically, right? It was derived by discussing the form of solutions a wave equation might take. And what we have found, this is of course a wave traveling, well, that has a z dependence. We haven't talked about traveling yet, but it has this form. Okay, and the whole point was it took on solutions of the type what? A cosine kz minus omega t plus some phase. Okay, and this is a cosine. We could have just as easily made it sine, or just as easily made it any function of this variable, of this single variable. This k and omega can be plus and minus. Delta can be a negative number. All of that is true. But if I were to graph this, it would look something like this. Because delta is positive, it would start off somewhere like this. Of course, I'm not good at drawing cosine functions. And this would be what? This would be when this is 0. So at t equal, this is of course at t equals 0. It's a time-dependent function. So this would be when kz plus delta equal to 0, or z equals minus delta over k. So this is minus delta over k. And because this is plus, the phase is backwards, right? And this means, because this is negative, it means it's moving with the speed. And v, the speed of the wave, is omega over k. These are the features we have seen. My apologies for the terrible cosine function. Oh, I know what to do. Maybe the correct thing to do would be to first draw the cosine function. And then draw the axes. This is F, this is Z, and this is minus delta over K. That's where it started from, so to speak. If delta is minus, the phase would be that way. If this is plus, the wave would be traveling this way. All right, this is math. We didn't talk about any physics at all. So what might, in nature, do something like this? Of course, we know the answer. It's electromagnetic waves, and because that's why we're doing it in this course. But there are other waves. So electromagnetic waves have the feature that there's electric field and magnetic fields. So, and they're both kind of waving, if you will, simultaneously. So to understand that, let's look at a simpler case. We'll consider the wave on a string, or the wave equation on a string. Well, we'll see. Waves on a string. So you have a string that is allowed to wiggle. And the reason I'm doing it this way is we're only going to consider the case where it is a pure wave equation. Otherwise, complications can occur. Okay? A string is not like an electromagnetic wave. There's friction and all sorts of things, right? So we're only allowed to wiggle the string a little bit. It doesn't go very high. Furthermore, if you look at the wave, each point in the wave can go only up or down. It's not going sideways. So at any point, even over here, it can go either up or down. But it's not moving sideways. So what I'll do is I'll consider one portion of the wave and sort of zoom it. And when I zoom it, I'll also make sure that the slope is very small and yet make it look a little curved. Okay, and let me draw an axis. And let me mark 2 points. This is the point Z. F of Z, but possibly of T as well. This is sort of a snapshot. So yeah, T equals constant, if you will. Just a snapshot. And what I'm going to do is I'm going to look at 2 points. So this, the string itself has a tension on it. As you know, a taut string, the tension is constant, right? So this tension force has some vector T. It's the same magnitude. So it's not here. Yeah, along the string, correct. The magnitudes are the same. And it makes an angle. And so this is the point Z plus delta Z. I will call this angle theta prime and call this angle theta for the moment. Okay? So by assumption, theta is theta or theta prime is very small. And we're going to consider the chunk of the wave that is in this region and see what equations govern it. So we're going to focus our attention to this portion, this much of the wave, right? And see basically the F equals ma on it. So there's a net vertical force. I'm going to write it as delta F. I'm not going to put any magnitude. Well, vertical mean, I'm not going to put any direction. Well, by vertical means it's the vertical direction. Net vertical force, delta F is T sine theta prime minus T sine theta. Look, the vertical component is horizontal is cosine, vertical is sine. Here it's T sine theta prime, here it's negative, right? So I'm going to bring the T out. I don't need to do that just yet. I could have done another step. We need another fact. What is limit theta goes to 0 of sine theta over tangent theta? Because I don't know how to calculate sine theta. You'll see what I mean by that. Well, that's easy. Limit theta goes to 0 of sine theta over sine theta over cosine theta, correct? And that's limit. This is one of the easiest calculus homework you could have gotten. Yeah? Yeah. I'm sorry? Why are we doing that? Yes. That I haven't explained.
Okay.
Seems like I'm just doing it, right? And I'm going to use this result and this result. Theta is 0. Is 0 a small number?
Yeah.
Good. Is that in this category? Good. So what I'm going to do, if theta is going to be very small and sine theta over tangent theta is equal to 1, what can I conclude? Sine theta is approximately equal to tangent theta. It is, you can try it in your calculator. As a matter of fact, sine theta is approximately equal to theta, because you have another limit. Sine theta over theta equals 1. So then what I'm going to do, Chip, your concern is absolutely valid. Yeah, I see it, but what are we doing with it? You just replaced sine theta with tangent theta. We have replaced, in the past, in freshman physics, and I think I gave you the hint away, we have replaced sine theta with theta. Do you remember when?
I mean, I know we did a lot in optics.
Okay, physics 2. Let me do one better. Simple harmonic motion.
Okay.
Maybe you've even seen it in classical mechanics. Simple pendulum.
I mean, we use the small angle approximation a lot.
Okay. All right. So now, why did I want this? Is small angle approximation sounds very useful. So replacing sine theta with theta looks like a very useful thing. But I'm replacing it with tangent. Doesn't seem very useful. But here is where it's useful. Tangent is the slope of the line. Yeah? Well, that's what tangent is, slope of the line. So I can write it as a differential equation, see? And at what point am I evaluating it? It's theta prime, so evaluate it at z plus delta z minus evaluated at c. Correct? That's what. Now, this, I should, this is the art in physics, huh? This is the rate of change of derivative. What is the rate of change of a function? It's the first derivative. This is the second, almost the second derivative. Isn't that true? See, if I have f of x plus delta x minus f of x over delta x, limit delta x goes to 0, that's equal to df dx. That means, for physics, when delta x is small, correct? I just took this delta x over there. So change in function is the derivative times delta x. Well, the change in derivative is the second derivative times delta x, or in our case, delta z. Fine. But we have another. I mean, that's fine. We just computed the force. But what is force equal to? Ma. Right? Delta Ma. What is M? Well, the mass contained in this much length. Well, that is mu times delta Z. That's the mass. And you might ask, what is mu? Mu is the linear mass density. Correct? Now I need acceleration. So this is the mass. This is the acceleration. So we have two expressions for delta F. They must be equal to each other. So then I have T delta dz squared delta C equals mu delta Z d squared F dt squared, or d squared F dz squared minus 1 over v squared d squared F t squared equal to 0, where v squared, so yeah? So, much like the simple harmonic motion, in that case, the waves on a string satisfy the wave equation. And the velocity of a wave on a string is t over mu. Applies to guitar strings, for example. So the abstract concept of a wave equation is actually realized in nature. So this would very much apply to a guitar string, because you're not plucking it like a bow. You're only just... So let's use this to understand a few things about waves, and we'll talk about waves on a string a little bit more to get a sense of boundary conditions and all of that. Any questions? Yeah? Questions?
Not so far.
Okay, good. So let's look at this expression. We'll try to use. So the good news is we don't have to solve the differential equation, partial differential equation. By the way, this is a partial differential equation. We don't have to solve these equations. We know the answers already. So that's what I told you. In this chapter, really all the problems are going to be algebraic. We have to match boundary conditions, and that reduces to algebra. Well, let's see what we mean. So we might want to consider something like cosine kz minus omega t plus delta. This is the amplitude, right? So derivative of cosine is sine, cosine is negative sine, derivative of sine is cosine. We might have to take a couple of derivatives. It's a hassle to take derivatives with sine and cosine. If I have something like this, what is it? Ik times e to the ik. Yeah. This is the coefficient that comes up. So again, it's calculus. I mean, it's algebra. Every time you take a derivative, the coefficient comes out, and you get that same function back. So no matter what derivative you take, you'll always have e to the ikx, e to the ikx. So what we want to do is not do calculus, but just algebra. So what we will do is we'll write this as, well, a times the real part of e to the I kz minus omega t plus delta, using Euler formula. So where did this come from? E to the I kx equals cosine kx plus I sine, right? So, and the real part is just cosine. That's where this came from. All right. So then what we will do is define, I don't like this delta, so what we can do, define a complex amplitude by A times e to the I delta. So then I would have f of zt to be the real part of a tilde e to the I. See, I got rid of the phase because that's just a constant. Might as well just bring it into the amplitude. Now, in this expression, again, it's all of this is by convention. A is the amplitude, right? Not A tilde, but A is the amplitude. And therefore, we will set A to be greater than 0. It's a useful convention. Amplitude is the maximum displacement. Well, maximum and the minimum is the same but opposite sign. So when we say amplitude, we mean the positive value. Just like, what is the square root of 4? 2. But if there are two numbers, right? But by convention, this is the positive root. So exactly that way, by amplitude, I mean the number that is greater than 0. And so, at this point, we'll say, well, let's forget about the real wave at all. I don't want to see this real part written out all the time. I'll just write a complex wave. And realize that the real part of the wave is just a real part on both sides. That way I don't have to write real everywhere. Okay? So this is typically the form that we will work with, and you'll see shortly that all calculus is just over. Well, what does that mean? What are we trying to do with it? Let's see, what's the next topic I should bring? Yeah. So what I'm trying to do, you know laws of reflection and refraction of light. We'll derive that using Maxwell's equations. But before we get to Maxwell's equations, let's do that in a string. So let's say reflection and perhaps even transmission. So what we will do is consider light reflects when it hits dielectric media perhaps, but we're not equipped to do light just yet. We're studying strings. So what we'll do is we'll make strings made up of two different materials. We'll take one and then connect it to the other. And this will be the point z equal to 0. Everything about this side is 1. Everything about this side is 2. In particular, while the tension is the same, this side might have a mu1 because it's made of a green string. This side will have a linear density of mu2. What would that mean? The tension in the string is the same because the string is not moving horizontally. So that means the wave on these two sides will have different speeds. Okay, and then what we will do is we'll tweak the string on this side. So you'll have an incoming wave. So you'll have an F incoming, incident. And it should be tilde. But gosh, I may forget to put the tilde sometimes. Remind me, okay? And at this point, when this wave comes in here, some of the wave would reflect and some of the wave would transmit. You can easily imagine that this side will start wiggling as well. So as a result, here you will get a reflected wave and you will get a transmitted wave. The incident and the reflected wave will have the same speed because it's the same linear mass density. The tension is fixed in the string, so the only variable is over here. On this side, the wave has to have a different speed. Fine. Now, let's imagine that the wave is doing what waves do. And this side is a superposition of the incident and the reflected wave, so it doesn't look like a nice cosine wave. It's a superposition. It looks something like this. And on the other side, it could be, again, we don't know what exactly comes out. And something like this. So whenever you study waves, you will see that the thing that determines how the waves wiggle are boundary conditions. In the case of light, it might be light that is incident on certain glass or prism. In the case of a string, in this example, it is the fact that it is two waves have been joined together. But boundary conditions is, first of all, the incident wave plus the height of the reflected wave should be equal to the height of the transmitted wave. If it's not, that means the string is broken. Yeah? Fine. So this is usually written in the sense that the total wave, zero limit, taken from the negative side, and we can use the real part. Right? The limit at z equals 0 from both sides have to be the same. But not only should the waves be continuous, it should also have the continuous slope. And to illustrate when this doesn't happen, I'll do a specific example. See, the derivative here, right, this derivative has to be smooth. So the derivative, you see what I mean by 0 minus and 0 plus? Yeah, as you take the limit of the derivative from this side and this side, they have to be the same. So this is typically, now f by f I mean the net on both sides, huh? That's what I mean. Okay, let's write down what incident waves and Griffiths presents a cleaned up version where you might stare at it and go, well, where did that come from? It's not altogether clear to me. So let me clarify. Again, I'm only going to do this guy. I mean, the complex version incident. So I would have some incident, e to the I. On side 1, it is k1z minus omega t. That is all you get to fix. Yeah? Then I'm going to write something that is wrong, then I'll change it. So maybe you shouldn't even. So the reflected, so then comes the reflected wave. This part, there's no argument. This part, there's no argument. As a matter of fact, let me do it this way. I k2z minus K1 and K2. T. See, I have not filled this in. Should I call this omega I, omega r, omega t? We may be inclined to do so, right? So if I do this, I would have that a tilde I, e to the I. I'm going to evaluate this at z equals 0. I'm going to use this condition. So let me call this I minus omega incident t plus a tilde r e to the minus I, or even, let me do it this way, reflected t should be equal to a tilde transmitted e to the minus I omega transmitted t. Is that correct? Because whenever there's a z, I'm putting a 0. Now, I put minus over here because it's moving to the right. I put plus over here because it's moving to the left. This is what we don't want. And I put a minus over here. And I made these three omegas different numbers. Yeah? AI is a complex number, constant complex number. It's just the amplitude. This is a complex number. This is a complex number. A complex number has how many independent components? 2, right? 2, 4, 6. This has to be equal at all times. But this guy oscillates like crazy. This will never happen. You cannot find three complex numbers if these numbers are different to work out. The only way this can happen is if this is that way you can cancel off the omegas. Because this has to happen over at all times. These are only 6 complex numbers. There are infinite values of time. So the only way this can happen is if all the omegas look like this, so that you can simply, so this can well, that's interesting. That means I have to do this, this. Well, that's fine. K1 makes sense, K2 makes sense, because after all, what is the speed? Speed is omega over K. So you'll have velocity in the first medium to be equal to omega over K1. And velocity in the second medium to be omega equal K2, sorry, not KZ. K2. Yeah? That works out. The two speeds work out. Fine. So the K1, K2, perfect. Omegas have been solved. Now, if I do this, and so I know that the magnitude, it has to be omega over K1. Yeah? It's plus or minus, right? But if I do it this way, which way is the wave moving? To the right. Which way is the reflected wave moving? To the left. The only way I can fix that is making this a minus sign. So now it will be omega over minus K1, so it's minus. We constantly talked about to make the wave move in one direction or the other, you need to change the sign of omega. In the very first example we do, that simply won't work out. You have to pick this choice. Correct? Now it's simple. We just apply the boundary conditions. It's just algebra, so let me make a mistake. Let me just calculate, huh? Or rather, yeah. The first one, all the time dependence have canceled out because it's every term has e to the I omega t. And the first equation becomes incident plus reflected equals transmitted. And then I have to take the derivative. Every time I take the derivative, I get a minus I K1. So I would get I K1 I minus what? Tell me, why did I get the minus instead of? See, I get IK1 here. Because it's a minus, I get a minus IK1, so that's the minus sign.
So wait, why are we doing
Oh, this is,
this? Oh, okay. All right.
so from 1.
Okay.
So see, here's the advantage. Now instead of taking derivatives, we just bring the factor up. Otherwise, you have to keep track of sine and cosine. It'll be impossible to solve. All things have vanished. Well, if this is true, chip, it's easily doable for me. Now the goal would be to solve for the reflected and the transmitted amplitude in terms of the incoming amplitude. Incoming amplitude, you don't have a choice. Somebody's plucked the string in some sort of a wave, right? So then, what I'll do is just, so these are the two equations. A tilde I plus A tilde R is equal to A tilde transmission, but I can solve that from over here. It's K1 over K2, A tilde I minus A tilde R. That's convenient. This is an equation of only A tilde I and A tilde R. Therefore, I can solve for A tilde R. You can see how the math works out very easily. And this gives A tilde R equals K1 minus K2 over K1 plus K2 A tilde I. If you're wondering how I jumped from here to here, that's not too complicated. Note that 1 plus K1 over K2 is nothing but K2 plus K1 over K2. And this is K1 minus K2 over K2. And then when you divide the other, what the numerator denominator flips, K2s would cancel. It just follows immediately. And if you play the same kind of game, if you know the reflected transmission, you can put it in here, you can solve for this, and you get similarly the transmitted is 2K. So we have computed both the transmitted term and the reflected term in terms of the incident term. I can write this in terms of velocities. A tilde R equals V2 minus V1. Notice something has happened. V2 plus V1. A incident. And this is A transmitted equals 2 V2. It's easy to go from K to V when you have these ratios. Every time there's a K1, you substitute it with omega over V1. If you do the algebra, that pops out. The omegas simply cancel. Well, fine. Now comes the interesting part. We have to get the actual amplitude, and more than that, I need to get the real amplitudes. I don't care about those complex things. I want to know what's the wave doing. So I have AR e to the I delta R. That's how we define the complex amplitude, to be equal to V2 minus V1 over V2 plus V1. AI e to the I incident phase, and transmitted is 2 V2 over V1 plus V2, AI e to the I delta. All right, so I'm going to consider two different cases. Case number one. Here, I pick mu2 is less than mu1. So let me try to visually draw that so that you understand what that means. Mu2, so mu1 is larger. Or not larger, denser. Doesn't the diagram suggest what I have written? Mu1. Yeah. In that case, what happens to the velocity? The other way around. Then V2 is greater than V1. Yeah? Because V is square root of t over mu. So if mu increases, V decreases, and the other way around. Fine. So that means this is a positive number. So because I want AI and AR to be positive, I can set AR to be equal to V2 minus V1 over V2 plus V1 times AI, and delta R equals delta I, and AT equals 2 V2 over V2 plus V1 AI, and delta transmitted equals, so all three waves so basically what did I tell you? All the amplitudes have to be positive. So if AI is positive, and this is the case, that's positive. Yeah? Okay, let's do the other one. You'll find that this is not quite the case. Case 2. Perfect. Case 2, obviously, mu2 greater than mu1, which implies v1 is greater than v2. The string looks, the diagram has changed. So here it is this string connected to, I know it's exaggerated, a denser string on the other side. Yeah? The only difference will happen here. I want AR e to the I delta R equals minus, I'm changing the order, V2 minus V1, I'm going to write it as minus of V1 minus V2, because this is positive. So what I'll do is I'll let this equal to the positive version of that. So I get AR, the transmitted amplitude is still positive. We want it to be positive. And then minus e to the I with this I can write it as e to the I delta R plus pi. Because what is e to the I pi? It's cosine pi plus I sine pi. Sine pi is 0 and cosine pi is -1. Oops. That means delta R plus pi equals the reflected is out of phase nothing happens to the transmitted. Transmitted is always in phase because there's no minus sign here. So the transmitted remains the same. And I'll give you a drawing. V2, I'm just copying from the other side. Delta transmitted is the same as delta incident. So what's happening over here? This is 0. If you have a wave coming in this way, yeah? The transmitted wave looks like this. It's in phase. But the reflected wave I guess to be color consistent. That's what's happening. Questions?
So it's just like the reflected wave is out of phase. And
Out of phase,
the
yeah.
transmitted wave is in phase.
Correct. So when the light reflects, it'll flip.
Okay, yeah.
Or wave in a string reflects, it'll flip. Right? So this guy goes in phase, the other one is off by pi over 2, because this expression has a minus sign.
Yeah.
And that's not pi over 2, pi. Yeah?